Hello, I'm Alex Jung, and I now explain our paper Localized Linear Regression in Network Data, which is joint work with my former PhD student, Ngo and Tran. The guiding principle of this work, or underlying this work, is to organize data and computation as networks. Such network data arises, for example, in meteorology, where weather phenomena or weather observations like temperature or precipitation is recorded at different weather observation stations all over Finland. And this this weather phenomena observed at different weather observations or observation stations might be similar if these observation stations are nearby or in a similar geographic area within the same valley, for example. So we model this as network data where each node here represents an observation station, for example, of the Finnish Meteorological Institute. And for each node, we know features. For example, we know the temperature during the last P days, which might be the feature vector associated with a certain observation station. What we're interested in eventually are the labels. For example, the prediction or the temperature for the next day. So this Y is the temperature for the next day at a certain observation station. And typically, we do not know these labels. So we do not have reliable estimates or predictions for the temperature tomorrow, but only on a small set of locations. And the corresponding nodes we collect in a training set M. So the goal then is to learn a predictive model, in the simplest case, a linear model, which takes the features, for example, the temperatures on the previous days observed at a certain station or node, and then delivers a prediction for the temperature on the next day. And in the simplest case, we model this relation between this label and the features using a linear regression model. So this is a linear model, which involves some modeling error or also measurement noise. All kinds of noises and errors are collected in this term here, epsilon I. So in order to learn these weight vectors for all nodes, so these weight vectors represent predictors. So having these weight vectors allows us to predict the next day temperature based on the previous day's temperatures. And learning this predictor is based on the idea, on one of the basic ideas in machine learning, that similar data points have similar labels, or more precisely, similar data points have similar models. So the models, in this case, a linear model that characterizes the behavior, the statistical behavior of the data observed at these observation stations, we postulate that these models must be similar for well-connected nodes. So this network structure is obtained by experts, by meteorologists, which say, okay, this weather station and this weather station, they are nearby. There is no mountain in between. So the general statistical properties or the model parameters of meteorological values or meteorological measurements like the temperature should be similar. And this similarity between, or the similarity in this model parameters or weight vectors between similar nodes is represented or quantified using the total variation. So we define the total variation of these weight vectors by summing the norms of the difference over edges all over the network. So we require this total variation, or we want to learn weight vectors or model parameters such that this total variation is small. And this small total variation, or the requirement of a small total variation, typically enforces these weight vectors to be constant over well-connected nodes. And in order to learn these weight vectors, we balance between two terms. So we balance between the training error. So we want to learn weight vectors that agree well with labeled nodes. So we assume for some weather stations, we have asked experts, which did a careful analysis of the weather situation and obtained some labels for some data points where we are really sure about the label. However, for most labels, for most data points, we don't know the label, but rather we want to learn a predictor for the label. So we want to learn the predictor or weight vectors for all nodes. And for this, we require a small total variation. And this is one instance of a network lasso problem. So a network lasso refers to empirical risk minimization using the total variation of the model parameters as a regularizer. And this network lasso involves a tuning parameter lambda, which allows to choose between focus on a small training error for small lambda and enforcing clustered predictive models. So choosing this lambda large enforces these weight vectors to be a constant over well-connected nodes. And in the extreme case, if we choose lambda extremely large, we enforce the solutions of this network lasso problem to be a constant weight vector. So we end up with a regular linear regression model, one single linear regression model for all observation stations. However, we are interested in learning flexible linear regression models. So this linear regression models might be different for this cluster and for this cluster. And choosing lambda right or using a good value for lambda will achieve this goal, as we will show in a second. So in order to solve this network lasso, we use a dual approach. So we use duality, which allows to define a dual problem. So we can define a dual problem, which is naturally associated with network lasso. And this dual problem allows to characterize the solutions of the network lasso via a coupled set of conditions. And these conditions look already like a fixed point equation. The only difference is that here we don't have equality, but the element symbol. So it's not exactly a fixed point equation, but it has already some structural similarity to a fixed point equation. And it turns out actually that slight reformulation of this condition gives us a fixed point equation. And iterating this fixed point equation provides us with an iterative algorithm, an instance of a primal dual algorithm, because this algorithm simultaneously solves or constructs a sequence that converges to a solution of the primal problem. So these weight vectors here converge to a solution of the network lasso. And at the same time, intertwined, it constructs a sequence of dual vectors. So these dual vectors are associated to edges in the network graph. Well, the primal variables are these weight vectors. So we have one weight vector for each node, and the dual variables are vectors associated with edges. And this algorithm, this network lasso algorithm, turns out to be highly scalable since it can be implemented as a message passing protocol. So these updates can be implemented by passing messages over the edges in the data network. And if we have few edges, if it's a sparse network, then we only have to compute a few of these message updates. So this is a scalable method. Okay, but we also focused on theoretical properties of the network lasso problem, in particular, under which conditions is the solution of the network lasso a clustered predictor. So when we have a synthetic data set like this, which is clearly structured into two clusters, and we observe the labels only for these filled dots, only for these 2 points, we observe labels, and we use the network lasso to learn a linear predictor for all nodes, under which conditions is the solution of network lasso clustered over these two clusters. So when are these predictors constant over cluster 1 and constant over cluster 2, which is what we would like to have, since there is a clear clustering structure in the data network. And it turns out that this clustering behavior depends on the connectivity of the labeled nodes of the training set to the boundary edges between the clusters. And we measure this connectivity using the notion of flows, of network flows. In particular, we require a certain amount of flow to be routable, so we require that a certain amount of flow, rho, can be routed over this boundary edge by respecting capacity constraints. And the capacity constraints are given by the weights of these edges. So we allow typically weighted networks where the similarity between nodes is weighted by some number. And using this flow to measure the connectivity, we come up with a condition which connects the network structure via this flow value rho and the properties of the statistical model. In this case, it's a linear model. And one characteristic of this linear model is the number of features or the length of the predictor vector or weight vector, which is P. So if this condition is satisfied, if there is a sufficiently large amount of flow routable or can be routed over this boundary edge compared to the number of features used in the linear models at each node, a network lasso delivers a clustered predictor. And we have verified this by numerical experiments, which are discussed also in the paper. So the threshold nicely shows up also in the numerical experiments. So once this flow is larger than square root of 2, so in this simulation we used only 2 features, so P was 2. If the connectivity is better than square root of 2, then the error so the discrepancy between the network solution and the clustered structure becomes smaller and smaller. Okay, so we have applied network lasso to learn a localized or a personalized, in some sense, linear regression models or linear predictors. We have implemented this network lasso using a highly scalable message passing algorithm, which is obtained from a primal dual method. And we have studied conditions under which the network lasso solutions are clustered according to the underlying cluster structure. Okay, so here is the paper or a snapshot of the paper, which has been published in the IEEE signal processing letters. Thanks a lot for your attention, and I would be happy if you check out my social media channels for posts on the topic of machine learning, in particular machine learning for network data. Thanks a lot.